Smashing. Right, the wonderful world of part A1 to section B. Okay, so we've done the whole mass on a spring, back and forward, frictionless table. Let's move it on now to a slightly more exciting one, which is talking about pendula, or in particular one pendulum, which is making small oscillations. So let's again draw the diagram, always very important. And remember, the main point of these questions is to find that all these systems react, or at least move according to this equation up here. And we'll find that out in a sec. So we've got a small mass on a pendulum moving back and forward from its equilibrium position here. So let's call this distance x, let's call the angle it's making with its equilibrium position theta, and let's call its length r. Okay, cool. So again, what we want to do is we want to take out the mass in question, what we're kind of working on, and let's draw a force diagram. So we're going to include gravity in this one, because gravity is essential to making a pendulum work. So mg is just straight down, and we've got tension, which is up towards the pivot point, so it's on the same angle as r. Now this is a case where people get a bit angry, because it's a bit of a cheat, but we'll roll with it. The question actually does say we've got small angle oscillations, and whenever you see the phrase small angle oscillations, you know you can make a couple of assumptions. Firstly, we can make an assumption that we have sine theta equals theta. That's the first assumption that we make. And the second assumption, again, slightly cheeky, is that T is proportional, give or take, well, not proportional, but it's pretty much equal to mg. In reality, we've got, actually it's T cos mg, but cos theta, when theta is so small it's almost zero, essentially becomes 1. Again, these are just two assumptions we take as read. We don't really question them. You can think about them some more if you like, but I mean the central premise behind, hopefully this one should be obvious. If not, graph it on Desmos. That's always good. With this one here, essentially it's the idea that cos theta tends to 1 as theta tends to 0. Cool. Okay. So T is roughly equal to mg. So now we're looking for this equation going that way. Looking for this part of the T. The tension, the force of the tension. So let's draw a force triangle out. I've drawn that upside down, never mind. A force triangle out like this, where T is the hypotenuse, and we're looking for the force going this way. Okay, and because we've got SOHCAHTOA going on, SOHCAHTOA, we've got angle theta here, we've got the hypotenuse T, so we know it's going to be one of these guys, and we've got the opposite, so we know it's going to be sine. So we know that the force going this way, this force is going to be equal to T sine theta. Okay, that's all great. We know that we can replace T with mg and sine theta with theta, so we get F equals mg theta. Okay, that's all rather exciting. Now again, we've got a bit of an issue with a minus sign going on. We'll sort that out in a sec. If you've got a minus in your working now, don't worry, it should all work itself out. I often find that negative things soon tend to positive if you give them enough time. So just up here, we're just going to make a few kind of trigonometric identities, if you like, with this one here. Nice and simple, that x equals r theta. Again, that just should be read, that should be known, that's to do with arcs of triangles. And by, justifying by r, we get theta equals x over r. Okay, so let's pop that down into this equation here. So F equals mg x over r. Now, this is where the negative comes into play, because you will see that the force is going left to right. The force is dragging the mass this way towards this thing. Dodecahedron? I don't know. Anyway, towards this thing. And the displacement of the object is actually towards the typewriter. You know, this is kind of like a fundamental of simple harmonic motion, is that the force is proportional to, but in the opposite direction of the displacement. So you've got displacement going one way, the force drags in another. Very equally, if displacement was going left to right, the force would be going right to left, hence the negative sign. Force, as we know, is ma, so let's chuck that in. We've got ma equals minus mg x over r. Let's cancel the m's. Make a the double derivative of x with respect to time. And they get minus gx over r, which hopefully should be looking rather good there. So we have x double dot plus g over r x equals 0. And this fulfills the equation we wanted at the very top here, where omega squared is g over r. Wonderful. Yeah, again, sorry, this step, if anything was unclear, acceleration is just the double derivative of displacement. So you've got x, if you derive it once, you get dx over dt, which is sometimes x dot, which is the velocity. And if we do that again, you get x double dot, which is the acceleration. Cool, so that's part 2, that's the pendulum. And we move on now to our favourite bit, which is the LCR circuit.